Good morning. I'm Bill Brinkman. I'm the director of the Office of Science, and I'd like to thank all of you for joining us at our third science lecture. Those of you who are here in the auditorium, as well as all of you who are watching online in Germantown. So we hope we have a good audience out there as well as here. I'd especially like to welcome our distinguished guest, Joe Incandela, and Secretary Stephen Chu. You'll hear from Joe and about the Higgs boson in a few moments. I'm proud of the work that he and so many others supported by the Office of Science did in the long search for this important particle. And their many contributions to the potential breakthrough this past summer. It's wonderful. Like you, I'm looking forward to hearing more about their efforts. But I'd first like to thank Secretary Chu for initiating this lecture series. This is just one of his achievements as the Energy Secretary, and I believe that he has accomplished many things in the past 3.5 years. We brought significant new resources to innovative approaches to the Department's research and development mission. We're breaking down stovepipes between our existing basic and applied sciences teams, and also launched new research models like the Energy Frontier Research Centers, the Energy Innovation Hubs, ARPA-E and ARPA-E. These activities created a new and exciting interest in solving the world's energy problems sustainably. Our investments in wind and solar power have put the country on track to double renewable energy over the past 4 years. We've partnered with the utilities, local communities, and other federal agencies to accelerate America's transition to a stronger, smarter, more robust power grid, including more than 30 smart grid and energy storage demonstration projects nationwide. Steve personally took responsibility for our response to the Macondo oil spill and the Fukushima nuclear disaster. In both cases, we managed to bring useful resources to the problems and help solve critical issues. Secretary Chu has led all this and more. So it's my pleasure to welcome him today as he introduces our speaker for today's science lecture. Please join us and welcome Secretary Chu.
Thank you. My pleasure to introduce our speaker today, Joseph Incandela. I'm just going to give you a brief bio, and then I'm going to try to give you a 5-minute synopsis of what he's going to, prelude to what he's going to talk about. So Professor Incandela is a professor of physics at the University of California, Santa Barbara. He got his PhD with Henry Fish at the University of Chicago in an experiment looking for monopoles. There was a potential candidate monopole reported a couple of years later that turned out not to be. And he went into hydrogen physics, worked at a Fermi lab in the 90s, then became a professor at Santa Barbara, started working at CERN, and he rose in the CERN ranks working on the compact muons solenoid collaboration, which you will hear about. And right now he has been elected the senior spokesman for that group. So you will hear about what they have been doing at CERN, at the Large Hadron Collider, not only that detector group, but I presume the other Atlas and others. But anyway, but let me tell you about what this is. So I'm going to go back in time. Way back in time, a couple hundred years. And when physics was first essentially being born in a quantitative way, we began to try to describe forces, like gravitational forces. And the remarkable thing about these forces is people began to realize that these forces had a universality to them, in the sense that the same force that was responsible for an apple falling on the Earth would also be responsible for the planets circling the sun and the dynamics of the galaxies and so on and so forth. So, or the same forces actually with a smaller mass should be there indeed on an atomic and quantum scale. So the gravitational force was something that would be universal over all scales, that goes over many, many orders of magnitude, all right? Which is something different. Usually in science, you think of something, it works in this range, and then it's not going to work everywhere else. So one of the most successful theories in physics in the later half of the 20th century was electricity and magnetism, which had its roots first unified by Maxwell around the time of the Civil War in the 1860s. And then there was a realization that electricity and magnetism were really a unified force, even though they looked very different. And then much later, Einstein came along and said, not only do they kind of look the same, they are the same, they're unified, and you can write a set of equations, but they're even more unified than you think in the following sense. Suppose you have, let's say, a coordinate system, an x-axis and a y-axis, okay? And in that coordinate system, you might say, where's my nose along the x-axis and the y-axis, right? It's there, and it's got an x-coordinate and a y-coordinate. But if you rotate the coordinate system, the coordinates change, the nose is still there, okay? And Einstein said, to the degree there's a magnetic field or an electric field, depends on the relative velocity of an object and the observer. And so by going to different velocity frames, it's like a rotation. And so the amount of the electrical field and the magnetic field are just like x and y axes, truly unified. Okay? With me so far? So that rotation was a rotation and transformation of velocity space. Then there were great attempts by Einstein and others to unify gravity and the electromagnetic force, and he did not succeed, others did not succeed. But then in the 60s, there came a thing, maybe you can unify the electric and magnetic forces with weak nuclear forces. These are forces responsible for radioactive decay. And what do you mean by unification? You mean exactly the same thing. You have a set of fields. So every force, there's now a field. There's an electromagnetic force, there's an electromagnetic field. We learned by electrodynamics that with this field are associated quanta or particles, photons. So you got a field, you got a force, you got a particle associated with the field. So the unification of the weak and electromagnetic forces where, okay, there were two fields that we knew about, the weak forces and the electromagnetic field. But in order to unify it, they had to postulate another weak field, one positively charged, negatively charged, and one neutral with the electromagnetic. Now, there are four of them. And guess what? If you rotated, you first construct this field mathematically. It would be very, very symmetric looking. Then you do a fake rotation to try to get the real fields, the electromagnetic field, the two charged fields of weak decay, and this new field that had to be postulated. And in 1978, strong evidence of the new field emerged, and the inventors of the theory got a Nobel Prize for it. Now, here's the problem. You started with these four fields, four forces, but the weak force is very, very short range. It only extended the kind of the radius of the nucleus. With a very short range force, we already know since the 1930s that associated with the particle associated with that field had to be extremely massive. Whereas the electromagnetic field, very long range, massless, photon massless, goes at the speed of light. So here we're in a conundrum. The three weak fields had to be very, very massive, but we knew that the electromagnetic field, no mass. You do the rotation, it doesn't confer any mass. Okay? So Peter Higgs and others developed what appeared to be a mathematical trick or confer mass. So the so-called Higgs mechanism was that trick, which Professor Incandela will talk about. It was not considered something, it was kind of a mathematical, I was doing my PhD work at the time, actually on this stuff. It was not considered really, it was a mathematical trick. Now, as time wore on, okay, where were we? Every force, every field, every force there's a field. With a field, you quantize the field. in so-called quantum field theory. Once you've quantized the field, you expect a particle to be there. Now these particles had mass. But the Higgs mechanism is something different. Because it's not the electromagnetic force or the weak force or the strong force. It's the coupling of any particle to the vacuum that gives it this mass property. Okay? So it's a very different type of particle than all the other particles, like the photons or the gluon force bosons or any of those others. Okay? So that's what makes it a little bit more special, which makes it a little bit more exciting. It was, so the discovery was a capstone to that, to this theory that had been developed beginning in the 1960s. And here's the deal. We want there to be a surprise in this thing. If this particle turns out to be the standard model, which he will talk about, this is not good news. It's good news that we figured something out, but it's not good news because if this theory turns out to be right, then we have some fundamental problems of where to go next. And let me finish by one final thing that brings me back to the universal laws of Newton. We know that our understanding of nature is inherently inconsistent. Therefore, at some level, it has to be wrong. And it can be described very simply. We believe our understanding of nature is derived from these so-called quantum fields and quantum descriptions and quantum field descriptions of nature. But we also have another pillar of science, general relativity. As you get to smaller and smaller distances, there are fluctuations that get larger and larger. And once you get so small, such a small dimension, these quantum fluctuations that we know are there get bigger and bigger, and they get and fluctuations in fields means fluctuations in energy, which fluctuations in energy is linked to mass. The fluctuations get so large that in that dimension, in that space, you go into singularity space in the sense that you now have black hole type of stuff. You have mathematical singularities popping up. So at that length scale, now where do you go? Okay, because space now becomes not continuous, all sorts of things happen, and the whole idea of string theory is to limit the size you can go. There's a fundamental size, and you can't go beyond that. Okay? Now, the amazing thing about this is it has to do with physicists' faith. If they think they got something, they're willing to extrapolate by, this is about 26 orders of magnitude. How many orders of magnitude? 19 orders of magnitude from where we are today. Okay? That's a lot. So just as, and so we know gravity, when you extrapolate to the size of the universe, so far seems to work. Going back down the other way, so maybe in all of that, maybe 26 orders of magnitude, it's not going to be consistent with our fundamental quantum theories. So we got a problem. Okay? But we want a problem that we can solve one step at a time. And so that's the exciting thing about this. Does this particle have all the properties it was supposed to have? Not determined yet. He will talk about that. But is there a sign of some new physics in a range where the current Large Hadron Collider or the upgrade to that or a new machine that the world can indeed build give us those answers? So with that, I think it was 10-minute introduction. It's my pleasure to give the remaining 5 minutes to Professor Incandela.
Hello, is it working? Okay. I hope to fill the details in a little bit. So this is a picture of the CMS experiment. I'll come back to this later. So for my talk, I decided to call it, and sometimes I do this, title my talk, Searching for the Genetic Code of the Universe. And discovery at the LHC is what I'm going to talk about. So to say that you're looking for the genetic code of the universe sounds pretty big. You know, it's like, let me explain to you. It may not be so big as you think. I had a graduate student friend and who was working on string theory at the University of California, Santa Barbara, where I'm professor. And I asked her, are you interested in what we'll learn at the LHC? And she said, no, not really. I said, really, why not? She said, well, it only pertains to this universe. So you know, this is actually a rather modest topic. Okay, before I get started, I have to tell you a bit about particle physics and the Standard Model. I won't be going into great detail on the theory, but let me just tell you some things. I have a lot of slides, so I have to move somewhat quickly. Okay, the Standard Model is took about 100 years, and it's a combination of quantum field theory and the discovery of many new particles. Led to what's something like a periodic table, a new periodic table of fundamental elements. And this is what's shown here. You have quarks, leptons, and the particles that carry the forces between them. As Carlo Rubio once said, 100 years and billions of dollars, and this is all we know. But actually, this is what we want. We want it simple. So this is a very simple view of things. And it's remarkable that the universe, in some sense, is this simple. There is a piece that's been missing, which is the Higgs. And it's a very important piece. And this has been one of the greatest achievements of 20th century science. There's no doubt about it. Now, interestingly, there are some strange things that we don't fully understand. These are the quarks, the 6 quarks, which have all been now discovered and studied. The top quark is incredibly heavy. It's actually heavier than a gold atom. And we don't really understand these things. Why are there the different scales and so forth? So there are many things we have to understand. So coming back to this table again, remarkably, this model is probably one of the best tested models in history. We've done hundreds of measurements, sub-percent level, everything holds up. What we see in the universe are these things. We see the up-down quark and the electron. The up and down quark are the quarks really that make up the neutron and the proton. So that's what makes up atoms, these 3 things here. In some sense, we do see the effect of this, but we don't see neutrinos. And yet there are sort of 3 sets of these particles. There's one missing piece, and that's the Higgs. That was the missing piece. We'll talk about that. It may still be, we don't know. But I'll tell you what we've got. Now, while developing this fundamental theorem, theory of fundamental forces and interactions, physicists hit a snag, and this is what Secretary Chu was talking about a bit. The particles that carry forces had to be massless, but the data seemed to say otherwise. Okay? We see that the weak force was very short range. And in fact, why do any particles have mass, and what is mass? We didn't have any way to explain this. Now, massless particles move at the speed of light. The speed of light, as you know, is 186,000 miles per second. We know that energy is related to mass. So if a particle has mass m, its rest energy is mc squared. But if a particle has momentum p, this is the actual formula that you use from Einstein's equations. And so if a particle has no mass, there's still this piece left over. The energy is equal to momentum times the speed of light. And this is the equation basically for a particle moving at the speed of light. So there was an ingenious idea that came along. Suppose there's a force field filling the universe that somehow slows particles down to below the speed of light. This would make them have mass. And that was basically what this Higgs field introduction was to be. So here's kind of a graphical representation of this. Particles are moving through the universe through the vacuum, we call the vacuum, and there's a field. There's this Higgs field that permeates the entire universe, and some particles interact with it more than others. And the more they try to increase their momentum, the more they interact. Other particles don't interact. The photon, for instance, doesn't see this at all. But all the other particles that have mass, all the fundamental particles, interact with this field, and it slows them down. Okay, is it a field or a particle? Fields have very small packets of energies associated with them called quanta, as Secretary Chu mentioned. Elementary particles interact by exchange of field quanta. So here I show, for instance, the exchange of a photon for the repulsion of 2 electrons, okay? This is not so hard to believe, okay? But it gets a bit more counterintuitive with more complicated processes. In fact, it gets very, very, very counterintuitive. So, okay, I already told you that E equals mc squared. Now, it turns out that a particle and antiparticle could just pop out of empty space and then return. We call this the vacuum, and this is a vacuum fluctuation, and then vanish again, okay? these are virtual particles, and it's a very important part of the universe. It has very far-reaching consequences. The structure of the universe actually depends on particles that don't exist in the usual sense, but did when the universe was very hot and very young. And in some sense, this is the reason we do what we do. We're trying to understand what particles could exist because they actually have an impact on the structure of the universe and particles that do exist that we use and see. So I'll show you some more on this. Now, for example, top quarks were seen for the first time at the Department of Energy's Fermilab near Chicago, and this is a top quark event from the early 90s. Now, what makes us so sure about the Higgs? The Higgs theory has predictable consequences. It predicts very heavy force particles that carry the weak nuclear force W, the W plus, W minus, and Z naught. In fact, it's designed to do this. These should have a mass of about 80 GeV, and the Z should have a mass of 91.1. The proton has a mass of about 1 GeV. So these are very, very massive particles, as was mentioned earlier. We should be able to find them and measure their masses. In fact, for example, the Z should decay to 2 muons sometimes. And we can calculate, we can take and measure the momenta of the muons and reconstruct the Z naught mass. And if we do this many times, we get a distribution for the mass values that has a very predictable shape. In fact, we predict the shape for many thousands of Z to mu mu events to look like this, okay? You have a peak at 91.1. This is what a mass peak looks like. There's some backgrounds. Actually, this is from top quarks producing 2 muons. But this is what we see. So we get very close to what's expected. We know that there's something that is engendering mass to these force carriers. And the Higgs mechanism, that as it was portrayed, it was a mathematical trick, but it worked incredibly well. It gives you exactly what you want. Now, moving on. There are fundamental connections, as I said before, between particles. Let me get some water. I'm afraid I have a cold, so I'm a bit dehydrated. There are particles that we don't see that have an impact on the particles that we do see. So the mass of the W depends a lot on the mass of the top quark and the mass of the Higgs, in fact, okay, through virtual interactions. And these are the kind of interactions I'll show you in a minute. And this is because a particle's identity really cannot be so well separated from the things it can transform into in field theory. So for instance, here you see a W decaying to a, well, not decaying, but actually transforming into a top and a bottom quark, and then back into a W, okay? This is one of many possible diagrams that determine the mass of a W. And the W, in some sense, is a top and a bottom, is a charm and a strange, all the time. All of these things are sort of happening in reality, but in a virtual sense. Similarly, a W can basically transform into a Higgs in a W and back into a W. So this is sort of the strange part of quantum field theory, and one of the things I have the hardest time trying to explain to people, but I think it's one of the most interesting things about what we do. There's a vacuum. We call this vacuum, you normally would think of the vacuum of outer space, if you took all the atoms out and all the light and so forth, as completely empty. But in fact, it's kind of a teeming foam of quantum possibilities. And when a particle passes through the vacuum, it actually can create and interact with it and become, if you like, a much more complicated thing. So it depends what determines the vacuum. What states can exist actually determine a lot about the particles that we see. Okay, so the upshot is, if you were to measure the top quark and the W mass very precisely, you could predict the mass of the Higgs in the standard model. And in fact, this is what we've done. We know the top mass now at a very high precision from Fermilab. We know the W mass also from Fermilab very well. And so we can plot the W mass versus the top mass, and with our uncertainties, we find that in this plane, we're basically expecting, well, I'm sorry, this actually shows you the measurement with its uncertainties. This is about 70% probability. That's where we think these two masses would lie. Now, these diagonals tell you what the Higgs mass would be, okay? The gray region was actually ruled out. I don't know if you understand this. Some plots sometimes are very difficult. But you see the diagonals. This corresponds to 114 GeV, 300, 1,000. Roughly 110 times or 114 times the proton mass, 300 times the proton mass, and so forth. We make these measurements, and it tells us the Higgs should be basically between these two red bands, okay? But the whole gray region was ruled out, okay? So we think, giving ourselves a little leeway, that the Higgs must be between where it was ruled out to about here. And that corresponds to the range from 114 to 185 times the proton mass, roughly speaking. And again, we know this because we know that the W is affected by the top and the Higgs. Okay, now the problem is there is one big problem. The Higgs actually solves a big problem. It explains why we have mass for these elementary force carriers, but it creates probably many more problems than it solves. Now, as I mentioned before, virtual particles contribute to the Higgs mass via these, what we call loop corrections, but it's really that the Higgs can transform into other particles, and here I show you, for instance, this is a classical diagram for the Higgs if it had no quantum interactions, but it has interactions with all of the fermions, all the particles that are in the standard model it can interact with in a virtual way, and that affects its identity in the way that I mentioned before. Okay? When you calculate the Higgs mass, you find that there's a correction due to this effect, which is huge. This factor lambda is the Planck scale, and it's about 10 to the 19th times the mass of the proton. So we find that as soon as we try to calculate the mass of the Higgs, it goes berserk, extremely high. And this is what's called the hierarchy problem. And there's something that's needed to cancel these effects out. Okay. Or the universe may, by chance, be unbelievably well balanced. It turns out that if you fine-tune all of the constants in the standard model, all the masses, all the couplings, and so forth, to about 30 decimal places, everything works out. But we don't usually run into those kind of circumstances in physics. If there's usually something that creates a state of balance, an equilibrium, not such a fine-tuning that would require 32 decimal places. Well, it turns out if you actually bring in a new set of particles with roughly the same masses, you get a cancellation if the particles are different spin. And this is essentially one of the things we think may be happening in the universe. Okay? We think, first of all, you have to have these partners, and you add these terms, you get a nice cancellation. There's a much smaller term that's left. It too becomes large, though, if the partners, these particles are much more heavy than these particles, you start to get fine-tuning again. But all indications are that these particles should be in the range of the LHC. And the question is, what are they? How do you get partners to all the standard model particles? Well, you can introduce a very basic symmetry and say that for every half-integer spin particle, particles have half-integer spin or integer spin. If it's half-integer, it's a fermion. If it's integer, 0, 1, 2, etc., it's called a boson. So if you ever wondered where those come from, these are two physicists, Fermi and Boson, and these are two different types of particles depending on their spin. So you need in this idea of supersymmetry, basically you create, for every particle that exists, if it's half-integer spin, you create an integer spin particle that corresponds to it, and vice versa. And this is what you get. You get a whole new set of particles. In some sense, it's like a mirror image of the particle structure of our universe. And this is one of the things we think is worth searching for. But I won't talk about that in great detail. I will mention a few things that are nice about it. We talked, Stephen talked about unification. If you look at the forces for instance, for the weak, strong nuclear force and electromagnetism, these coupling strengths, which are universal, they depend on what energy you're working at. The strength actually changes with energy. And if you go to higher and higher energies, which is basically going back toward the Big Bang, this is what you get. They kind of don't get very close. If you introduce this supersymmetry, they actually merge to a point. And one of the greatest physicists I know, Ed Witten, said this is, for him, the most convincing argument why supersymmetry may really exist. So this is one other thing we're studying at the LHC, and as Secretary Chu mentioned, if we only see a Higgs now that has only the properties of the standard model, we don't know how is it how is its mass being tamed? How is everything working? How is everything so well balanced? What we'd like is to find some indication that it's not standard model, and some indication that it may be represented by something in supersymmetry, for example. So there is something worth mentioning, though. Supersymmetry generally predicts that there exists a Higgs particle that's very much like the standard model Higgs, but very light, under 130 GeV. And remember, the range that hasn't been ruled out for the standard model was 114 to 185. So things are kind of lining up. There's one other thing. There's a connection to dark matter. As you may know, I think there was a talk here about dark energy not long ago. It was observed that if you look at stars and see how they're moving in galaxies as a function of the radius from the center of the galaxy, you'd expect that as they get further and further away, they would be less connected and move more and more slowly along a line like this. But in fact, this is what's been observed, that they actually increase in speed. It's as if there was some heavy material that was holding them all together like rice pudding and spinning them around. And so we believe, and there's a lot of evidence now, that the universe has this material, which we don't know what it is, called dark matter. So, moving to the dark side. I'm almost done with the theoretical part of the talk. We know that about 5% of the energy in the universe is ordinary matter. That's all. We're really in the minority. We know we've done all this work and thought we understood everything, but it's only about 5% of the universe, so we're really not doing so great. We have to do better. 25% is dark matter, and SUSY theories, supersymmetry theories, predict exactly this, if you like. This was kind of a miracle, they called it at one point, that the supersymmetric theories not only predicted this beautiful unification, not only solved the problem of the Higgs mass, but also predicted dark matter at about the right abundancy. But there are other possibilities. SUSY is the favorite. As I said, it produces nice dark matter candidate, leads to the universal forces. It fixes this hierarchy problem with the Higgs. The remaining 70% is dark energy, okay? And I think it's fair to say we have fewer good ideas about what this is, although it's evolving rather rapidly. But it'll probably be taxed someday, for one thing. Department of Dark Energy? Has that been mentioned? No. Solid. Anyway, okay. Okay, or maybe not, all right? The absence. Frankly, we've been searching for supersymmetry for years, and we have no evidence at all, none. And some theorists are quite depressed about this. We've looked at every accelerator, we find nothing. And that means maybe it's something else. And there are many theories that have appeared to try and fix all these problems. Usually, they're like supersymmetry in introducing new particles that balance out this problem with the Higgs. But sometimes they introduce new spatial dimensions. And they do that because if you do add small spatial dimensions that you can't see, it turns out it makes this very high energy scale that I mentioned come very far down. And then the problem kind of disappears that way. So one way or another, either we have a mirror image of all the particles or we have additional dimensions, we think, to solve this thing, or else everything is extremely well balanced by chance. Those are the three options. Okay, so there are lots and lots of theories that try to solve all these problems. And we're studying all of them, actually. And in fact, if you don't know exactly what you're looking for, a Large Hadron Collider is actually the very best tool you could use, and that's what we use. So let me show you a picture. This is the LHC accelerator complex viewed from the Jura Mountains. And so you can see how enormous it is. This is the actual LHC, this yellow line. This purple line is a smaller accelerator that is used to inject into it, and here's another one. Here's Mont Blanc. My house is right over there. But it took many, many years to paint those stripes, by the way. That's one of my favorite views. Now, there are two really big experiments. Here's another view, and actually you get a better feel of how big this thing is, because this is the Geneva airport, okay? So it's really huge. And there are two multi-purpose detectors called Atlas and CMS. I'm the head of the CMS experiment, and I'll talk about both. Very, very balanced. Mostly CMS, of course. But, and then there are two other experiments, LHCb and ALICE, I won't talk about. These are doing very interesting physics, but it's very, very specific problems that they're trying to solve, which we are also trying to do in these two big experiments. And this shows the complex. There's a little linear accelerator that goes to a booster ring, to another ring, to another ring, and finally into the LHC. And the reason you do that is the energy range you can push particles depends on how far you can change the magnetic fields of your magnets in the accelerator. And typically, it's a factor of 10 or 20. So to get to very, very high energy, you need many stages. And this shows what those stages give you. Now, I'll tell you some facts about the LHC, because it's pretty amazing. This shows the two beam lines, actually, in a dipole magnet. It's all one magnet system, but there are two beam lines side by side. Okay. For the tunnel, it's 3-meter diameter, 16 miles around, and there are 2 billion pounds excavated. For the beams, they're made up of bunches, and they're separated by 50 billionths of a second, which is about 15 meters right now. In fact, they'll cut that in half pretty soon. Now, at the interaction points, the bunch length is pretty small, and the beam radius gets squeezed down to less than 1,000th of an inch, which I think is pretty amazing to have a machine that's 16 miles around and then be able to do something at the level of 1,000th of an inch. And this is a branch of physics I don't really participate in, accelerator physics, but it's really quite amazing. And the rates at which we have collisions of these bunches, about 32 million per second eventually, but at the moment we're running at about 16 million per second. Okay, I won't go into great detail here, but just to say that everything is kept very cold, 1.9 degrees absolute, so it's the world's largest cryogenic system. It's colder than space, and it's emptier than space. And it's like Swiss chocolate. You're wondering about this, aren't you? Okay, so the magnets, if we go to the highest energy possible, each of these magnets, of which there's over 1,000, stores about 7 million joules of energy. Together, it's 10.4 billion joules, okay? This is way beyond any previous accelerator, and it's enough to melt. That energy is enough to melt 12 tons of copper. And it's the kinetic energy, actually, of an A380 moving at 700 kilometers per hour. The energy stored in the beams, actually, if you look at one bunch, the kinetic energy is 129,000 joules. For all the bunches, you're up to 362 million joules. That's equivalent to 90 kilograms of TNT, or 15 kilograms of chocolate. I bet you didn't know chocolate had so many calories. And then what happens is the two beams, they get squeezed. This shows an actual simulation of what the magnets do to squeeze the beams. They fire them at each other and they cross. And it's equivalent geometrically, but at a much smaller scale, to, they say, shooting two knitting needles from either side of the Atlantic and having them hit head-on halfway over. And that actually is done by devices that were built in the US. In fact, there are many US contributions. I won't go into all this detail, but these focus magnets came from Fermilab. There were separators from Brookhaven. Many operational contributions, and almost all the R&D for future accelerators is going on in the US. Okay? Okay, I move on to the experiments. Atlas and CMS. This is Atlas. All the slides I got from for Atlas are from the spokesman of Atlas, spokesperson, Fabiola Genotti. So these detectors are very complex. They're the most complex ever built for our field. They're the largest. It's a very big jump in technology. To give you an idea of how big this is a person. Okay, so it's a very large detector, about 45 meters long, 25 meters tall, very fast response, and can handle a huge amount of data very quickly. And I'll tell you a bit more about this. So let me show you Atlas as it was being built. This is the cavern in which it was installed. These are people for scale in 2003. And then you see how it goes together. Voila. And there's a person. So this is a huge detector, and all of this now is filled also with detector elements. These are big collaborations, many, many countries. In fact, there's about 38 countries, 176 institutions, 3,000 authors, about 1,800 are PhDs, about 900 graduate students on this experiment. And then you can see US Atlas is 44 institutions, about 600 authors, and 170 graduate students. And this shows you the distribution. It's not a vote map. Now, let me tell you about my experiment, or at least the one I'm leading at the moment, compact muon solenoid. it was interesting because we had to build it on the surface and then lower it. So it had to be built in pieces. And so it's rather modular. And it's rather small compared to the other one, actually. It's very compact because we have an extremely strong magnetic field. The key is when we collide particles, new particles come out. We turn all the energy of motion of the two protons into energy to create new particles. And the particles are charged, they come out. We use magnetic field to make the particle trajectories arc. Okay? They get bent. And the curvature tells us their momenta. So we really need to know that. These particles that we're producing are so high energy that it's quite hard to bend them. Okay? So either you use a typical 1 Tesla magnet, say, and a very large distance in order to see the arc, which is what Atlas does to some extent, or you go to a very, very strong magnet. Okay? We go to a very, very strong magnet, and this allows us to bend the particles' directions in a much smaller size scale. And in fact, it's not even that small, but our detector is much smaller than Atlas, but you can see this is the magnet, so it's not so small. Okay, and this is the last time the detector was actually open. This is a view looking down at the central region. Okay, let me give you a quick tour of CMS. I don't have the nice collage of photos, but this is the cavern when it was empty, and this shows when we lowered these pieces. This is 2,000 metric tons, about 4 million pounds. Had to be lowered with a huge crane, and there are 4 straps. There was a high school, I gave a talk on this once at a high school, and some high school students said, what did they use for these straps? And I said, I have no idea, I really don't. I went back and discovered that the straps are each made of 55 steel cables over an inch thick that go to separate reels that are monitored by individual engineers so that they actually form the strap as they lower it, and they monitor all the tension so that they don't create any torsion or swing, because we only had 3 centimeters clearance on either side. So it's pretty amazing. There's many, many interesting engineering feats. Now, we actually turned some brass casings from the Russian military, it's a happy guy, into our hadron calorimeter, okay, as you see here. And this is, a calorimeter measures calorie, it measures energy. Okay, I mentioned this. This shows you the cabling and cooling lines coming in. This is like, was over, it was a bit of an oversight. We just said, oh, we'll be able to take care of that later. It took about 2 or 3 years of engineering and 50,000 man-hours to lay all this out. And this shows the last pieces getting installed, the tracking system. And then we're ready to close, and this is what it looks like closed, which is not very pretty at the moment. But that's how it is at this very moment. Here's the beam line coming in. There's someone on the other side doing the same. This is the collaboration part of it. It's only about 1/8 of the people involved. This is a life-size photograph of the detector. And we have about 4,000 scientists, 800 PhD students. I'm sorry, 4,000 includes engineers. We have about 3,000 scientists, like Atlas. We have 41 countries and 190 institutes. And this shows the US distribution, 48 institutions, 450 PhD physicists, and about 200 graduate students. Okay. Now, interestingly, Newsweek came out a few years ago with this, saying, it's the biggest experiment ever, and it's European. And of course, the news always gets it wrong. First of all, Atlas is bigger than CMS, and this is a picture of CMS. So they screwed that up. Second of all, here I say the US is very much welcomed by the Europeans. But second of all, actually everything you see in this picture was built in California. The US has a big contribution. We're the biggest contributors to these experiments, about 1/3, 1/4 to 1/3 of the equipment and about 1/3 of the people. Very big contributions, as I mentioned, to the LHC, and we really thank DOE and NSF. It's really been a fantastic experience. There are also many US labs and universities involved that contributed. Anyway, so how do we reconstruct what happened in the collision? This is the more practical end of things. Let me just show you. This is the detector before we put an end cap on it, and I thought it was a good picture to show because you see the cylinders. And basically, we just have nested cylinders, many, many of them, and as the particles move through them, we get signals, either to track the particles or later to try and stop them and measure all of their energy. So this is kind of a little cartoon diagram of what's going on. And you see you have many layers. On the innermost layers, we use silicon detectors, very, very lightweight, and we try not to deflect the particles. We want them to move through without almost seeing nothing, okay? We want to actually measure their trajectories in the magnetic field. We look at the bending, and we get their momenta. Then we put them in the path of basically lead tungstate crystals, really heavy crystals, which will stop any kind of electromagnetic particles, namely electrons or photons. And that's this region here. You see, you have an electron, it basically stops, it showers tons of energy, and we measure that energy very precisely. If it's a hadron, which is like kaons, pions, protons, something like that, we use the brass. The picture you saw before, the brass stops them. And the only thing that gets through everything is a muon. And so if I go back here, all these red chambers out here, the red is iron, the silver are detectors for particles, and those will detect muons. That's basically how it works. And very close to the beam, we have a super high resolution pixel detector with about 70 million pixels that we can use to actually measure things so precisely we can tell if a particle traveled a little distance before decaying. So we can actually measure lifetimes of particles to about a trillionth of a second that way. This is the first collisions on March 2009. This is me. I was running the operations for the experiment, and the press was supposed to stay back there. But if you tell the press to stay somewhere, they don't stay there. So this guy snuck up behind it was from Reuters, from behind all of our control panels and managed to get this fisheye picture of us. So we collide beams, okay? So we have two beams circulating opposite directions with 1,380 bunches at the moment. Each bunch has 160 billion protons. The bunches cross at 4 places. And in fact, despite the fact that they're squeezed to only 1,000th of an inch or less, and despite the fact that there's so many protons, we only get 20 to 30 pairs actually colliding. Protons are very small. And so you get a collision. And most of the time, they're not very interesting. The protons break up. It turns out quarks can't be separated. As soon as you try to pull a quark out, it creates a new one to pair up with it. So you get processes like this, where you turn quarks into various kinds of hadronic particles, nuclear particles, that don't live very long themselves. Let me show you what one of our first events looked like, just so you get a picture of what's going on, because it's important that you visualize them. This is happening 16 million times per second, okay? This is one of the first events we took this year with the highest energies. So you see all the layers of the detector there. The bunches cross, and that's what happens. We have 20 proton pairs colliding, and all of these particles come out. And that's a real event, and we really can reconstruct all that and with that kind of detail. So now, more interesting events are when you have a very hard interaction. The protons just don't break up, but the quarks inside, or the gluons inside, actually collide very high energy, and you can produce interesting things like a W, which I told you about before. This is a Feynman diagram showing a U and a D bar quark interacting to produce a positive W, which decays to an electron and a neutrino. And let me show you even a more interesting event. This is a Higgs, possible Higgs event. It's a candidate Higgs event. Very possibly, in fact, this is a Higgs event that we saw, where the Higgs decays to 2 Zs, and the 2 Zs decay to electrons, 1 to electrons, 1 to muons. It's a bit of a mess, right? How do you dig this out? Well, let's see if I can stop the thing. Probably can't. Did you catch that? Well, what happens is, let me do it real quickly again. You see lots of tracks that are curling a lot. They're not very energetic, but you see these colored tracks here deposit lots of energy only in the electromagnetic section or only in the muon part of the detector. In fact, yeah, so I don't know how to stop that, but we know that that is a pair of Zs. We can reconstruct the 2 Zs. By the way, I just show you heavy ions because it's cool. When you smash 2 lead ions together, it's quite a spectacular thing. These are 2 very, very high energy lead ions that collide. And for us, what's amazing is that the detector can actually handle that. There's never been detectors in the past that could do that, to my knowledge. Okay. It's a camera. We often call it a camera. It takes a picture. It has many, many pixels. So you can think of it as these detectors as cameras. They have 80 million pixels. But they're obviously not ordinary cameras for several reasons. They're designed to take up to 40 million pictures per second, which is pretty impressive. The pictures are three-dimensional. They're extremely precise to a few microns, a few millionths of a meter. And at 15 and 31 million pounds, they're not very portable, these cameras. But they're pretty good. Now, the challenges are that we have these 16 million times per second, and if we were to take each of those events, which is about, I don't know, a couple hundred kilobytes, you can imagine how much data we'd be collecting. We just can't handle all that data. So what we do, in fact, is we look for the more interesting ones, which are rare. For instance, the Higgs are 1 in a trillion, basically. But we look for not something that rare, but we look for very rare things that are interesting. And we keep only about 1,000 events per second, okay? That's all. So we have to pick the good ones, and we have to pick them fast. So we use triggers. And the triggers, basically, first, we do kind of a millionth of a second analysis, very quick, and we decide this is interesting. And if it is, we keep it. And we keep about 100,000 per second, and we feed those to a farm of about 10,000 computers, which each have about 1/10 of a second to say, is it worth keeping or not? And we keep the 400 to 1,000 best of those. And we still end up with lots of data. We have about 22 petabytes per year of data that's distributed around the world. You can see the distribution. And I think I have a little, yeah, this is for CMS. It shows you how we distribute data. First, we have, from CERN, we go to 7 giant computing centers. One is in Fermilab. And from those, they go to a set of smaller ones around the world. And then from those to yet a smaller set. So we have something like 100,000 processors working for us at any given time. And remarkably, we can get the data distributed worldwide in 6 hours, which is pretty impressive, I think. Now, I won't show a lot of results. I don't know how well you read plots and so forth, but the point is here, this shows kind of the rate at which this process occurs. Bigger numbers means it happens more often. And this is the production of W's. In this plot, at least, it's the most common. Then Z's, then top quarks, single top quark instead of a pair of W's, a W and a Z, a W and a top quark, 2 Z's, more and more rare processes. These are factors of 10. And we studied these, and you can see where these orange bars are that are horizontal, that's what's predicted. And these little blocks are what we actually measured. So we did the same thing. We have very fantastic agreement, also in CMS, same idea. So we understand all of the processes we should understand, and we measure them all as we expect. So this allows us to move on to the Higgs. So Higgs searches. Excuse all the graphs, but it's hard for us not to show graphs in my field, but don't worry if you don't follow them very well. The basic idea here is that we have a theory for the Higgs, which allows us to predict everything you could possibly know about it, but its mass. We don't know its mass. So at any given value of the mass, we could tell you, for instance, how frequently it's produced and how it's produced. For instance, this red line corresponds to 2 pairs of gluons actually fusing into top quarks to generate a Higgs, which sounds pretty far-fetched, but we think it's real, and there's indications that it works. There's another way you can actually fuse 2 W's or 2 Z's, and they kick out a Higgs. So these are different production modes, and you can see as you go to higher and higher mass, it's less and less likely you produce them. And then when you produce them, again, depending on the mass, they will decay different ways. So it's a somewhat complicated animal. If they're very, very massive, they can decay to very heavy objects like W's, Z's, and top quarks. These are the most massive particles we knew of. But if it's light, it can decay also to light particles. So in this region, which is where we said it would be most likely to be found, you can see we have the most complicated set of different decays. By the way, all these different curves add up to 1. So it's just saying there's a 100% probability it decays to something. This is the relative proportions into different things. And this is how we'd look for it. If it decayed to 2 photons, we'd have a huge background as a function of mass of just random pairs of photons, basically. But the Higgs would appear as a little bump. Okay? Same thing for Higgs decaying to 2 Z's. We'd see if the 2 Z's decay to 4 electrons or muons, we can reconstruct it and it makes a peak. So part of what we do are look for bumps, as I'd shown you before for the Z, looking for bumps for the Higgs. And I will show you the bumps that we found, and they're pretty small, okay? But they're very significant. All right, I don't know if I'm going to go through this in great detail, but what we did, this is an old plot from basically about a year and a half ago, or less, where we'd searched for the Higgs, and if we're a standard model Higgs, it should be along this red line, And we predicted our sensitivity could be looking for something that's produced even more rarely. Okay, so as you go down, it's more and more rare produced. And the black line shows you where we actually kind of sit with our experiment. So anywhere you see the black line below the red means we can rule out the standard model Higgs at about 95%. So you see there's a big range over which we ruled out the standard model Higgs. Up here, though, where it's above the dashed line, what we're observing is much higher than we expected. Okay, from just background processes, this tells you there could be something there. I'm going to skip through this. So these are more recently what we showed at the end of last year in CMS. This shows you, again, we can rule out everything where the black solid line is below the red, so big range of the mass. But there's something here, which now I've blown up, and you can see the data somehow is much higher than you'd expect if it were just standard model backgrounds, okay? So we're seeing some excess of events around 125 GeV, but it's just a hint. Interestingly, though, Atlas saw the same thing. About 125, we see a bit of an excess, but it was very statistically insignificant. So we made no major claims about this, and we moved on to 2012, and we started looking. But at the end of last year, remember I showed you before that we thought that the range that was available was sort of 114 to 185. With these experiments, we had ruled out a lot more. And interestingly, this is green region here was predicted by Fermilab. This is, again, the W mass versus top mass and the Higgs bands. And we'd wiped out this whole region here that's white. And the only place the standard model Higgs boson could sit is right here, which is about in the range of 115 to 127. So that's where we decided to look very carefully. This was the main story last year, by the way, that we squeezed it into this little tiny space where it could live if it's standard model. And that's what led us this year to really focus on that region. So I'm going to show you our results now very quickly. Again, it's a little technical to show these things, but I hope you'll follow it okay. So we saw these tantalizing hints of an excess. So what I want to show now is the cases where we would see a bump, mostly. Higgs to ZZ, Higgs to 2 photons. I'll show results for W's, but W's don't give you bumps, so I'm not going to spend a lot of time on those. Anyway, this is a display of an event in Atlas for Higgs to 2 photons. Here you can see a map of the energy, and this is kind of phi versus angle theta, but you can see the 2 photons produced here. What we're dealing with, though, are many, many interactions. And the photons have no charge, so we can't track them. And we have to figure out which one of the interactions they came from. So that's one of the complications. It makes it very hard. You have to know where it was to within about a centimeter, which doesn't sound too bad, but all of this activity that you see here is within a couple of centimeters. So you want to try and find out where the photons came from, which proton-proton interaction. This is an event in CMS. You can see lots of debris from the proton, and then 2 photons just really back to back, shooting out like this at about 125 GeV. So this is a really interesting event. So we look, and this is a probability plot. Now, if we see an excess of events, we can ask, what's the probability that just background events would produce this, not some new signal? And what you find is that if we combine the 2011 data and the 2012 data, the probability is extremely low. We're less than, something like 1 in 100,000 or something like this. So, or 1 in 50,000. So this is where we stood on this case, and you can see if you look at it in terms of standard deviations, it's more than 4 standard deviations. So this reaches the point where we really think we have something. But this was done also using statistical tools, and it's hard to visualize it, okay? So what we do is then we combine the data for all the channels, and sure enough, right at about 125, we see a bump. It's a rather tiny bump, okay? But it's a very significant bump, and there's nothing else like it anywhere else. So this is our strongest evidence that we found a new particle. Atlas has similar results. You see a very nice bump, okay? These are just 2 different expressions of the same data. And they also calculate that for this to happen just from background is very, very improbable, about 4.7 standard deviations, 1 in almost a million. Okay? And this shows you then the next search that we look at carefully, which is the Higgs decaying to 2 Z's, and the 2 Z's each decaying to 2 pairs of electrons or muons. And this is a beautiful event in Atlas where you have 2 electrons. I think these are actually all electrons. Okay? These 2 match up to 1 Z, and these 2 to the other Z. And again, we look for a bump. Now, you get a bump here from just standard model production of pairs of Z's. What we're interested in is to see if there's a bump somewhere below. And you see, in fact, there's a very nice little bump here at 125 again. So now we have indications of something in 2 channels. This is this little bump, but it's weak. It's not huge. Okay? So this shows you the results. Atlas now has been able to rule out all of this region that's in red. And this shows the probability for those events to be background events for the Z's. And it's about 1 in 10,000, something like that. This is an event with 4 muons, 2 Z's in CMS. And CMS also looks for a bump, and we see a little bump, also at 125. So you see we're seeing in both of these experiments, in both of these channels, little bumps, okay? But they're exactly at the same place. And when you add them all up, you get a very significant, statistically very significant result. Here I show the CMS result. It's very improbable that this came from background. The lower this dips, the more improbable it could be from background. So if we combine those 2 channels in CMS, you get 5 standard deviations. And that's the kind of the official level for discovery. Our expectation was about 4.7. Atlas, similarly. In fact, if they add in the W's decaying to electron, muon, plus neutrino, they get 6 standard deviations. And that's what you have. This is CMS adding in the W's and all the other channels. We still stay at about 5 standard deviations. Okay? So these are the final results. Very improbable that this could be coming from background. We both see excesses at about 125. In both cases, extremely improbable. Voila. Now, what's interesting to look at is how things match up to what you expect for the standard model. And I think I'm almost done. But you see, in both experiments, actually, Higgs to 2 photons tends to be much higher than what you'd expect for the standard model. That's this dashed line here, or in this case, it's this black line. About 1.5, 1.8 times higher than expected. And that was true in both years. If you dissect the data into 2 years, in both cases, it's high in both experiments, both years. Atlas has not yet looked at Higgs decaying to spin-and-a-half particles. CMS has, and interestingly, we don't see much indication. Although the errors are very large, we're basically at 0 here and a little bit above 0 here. So this is actually what we're working on now. We're trying to get more data. We have lots more data. And by the end of the year, we'll have 3 times more data. These error bars will get much smaller, okay? And referring back to what Secretary Chu said, if it's standard model Higgs, all these things should start to line up with this number 1. Basically line up with 1 here, line up with the dashed line there. But if we stay high, okay, for instance with the photons, and the errors become very small, then we have a very significant discrepancy with the standard model. And that would be very exciting. Difficult to explain, but extremely exciting. Similarly here, if the taus stay at 0, and the decays to fermions, spin-and-a-half particles, don't occur, that means we have something very exotic. At the moment, though, everything is still consistent because the uncertainties are large. So we can't yet rule out that it's standard model Higgs. All right. Other things we look at are the mass. These plots just show you the probability as a function of the mass. These are contours in probability of signal versus mass, and you can see that we measure, the 2 experiments measure around 125 or 126. Atlas is 126. We get 125.3, very close. The uncertainties, though, cover, so we're consistent. The next thing we want to do, let me mention, Fermilab also has some evidence. They look for Higgs decaying to BB bar, for example, or to WW, and they see quite a big signal in the same region for Higgs decaying to BB bar. So this is corroborating evidence. The big question, though, to tell us whether it's a Higgs or not, is whether or not its spin is 0. Okay? This is a big issue. And we know its spin has to be integer, because it's decaying to 2 photons. It has to be, in fact, even. So it's either spin 0 or spin 2. And the question is, can we separate these? And these plots just show you, to some extent, how well we'll separate by the end of the year when we have this much data. Ignoring the plots, you can look at just the standard deviations, if you like. We think we'll be able to tell 0 from 2 at about 4 standard deviations. And I think if it turns out that it's 0, then we'll be sure it's a Higgs. And somebody will probably get a Nobel Prize. Not me, but somebody named Higgs, perhaps, I don't know. Now, to know it's standard model or not will be very hard. In fact, the Large Hadron Collider, we won't be able to tell that. If it continues to look standard model, no matter how far we go, we won't be able to say with 100% confidence that it is standard model. Because there are many other models that predict a low mass Higgs particle that is very much like a standard model Higgs. All right, so we just submitted our papers last week. New boson has been found. It's 48 years since this was predicted. It's 20 years it took us to design and build these experiments and accelerator. It was 3 years to acquire the data, and a generation of intense effort for about 6,000 physicists to get this data, which is pretty remarkable. So what's next? We got to figure out what it is and see where it may take us. And in fact, the Higgs may be a portal to new things. This is one thing we're trying to understand. If it's not standard model-like, it could guide us in trying to understand how to answer all of these other questions that I mentioned. Anyway, stay tuned. Thanks very much. Is there time?
All right, thank you very much. And now open up to questions. Come forward. There's maybe some remote people also, I think. But any questions?
The gravitational field is well, everybody knows about it, and you can. Why is it so difficult to quantize it? And the properties of the graviton if you do quantize the gravitational field.
You're wondering why we can't have a quantum theory of gravity, you mean?
Where does the graviton fit in this this model, in the standard model?
It doesn't. Gravity is not really in the standard model. And string theory is trying to figure that out, how to make a quantum theory of gravity and bring it into a single model. But when we talk about the standard model, we tend to just not even mention gravity because it's not part of anything we could really see or detect unless there were very small extra dimensions, as I said. Then there's a possibility we could detect those. And we have searches at the LHC for those. We haven't had any sightings. That's how you produce miniature black holes, for example. And we have searches for those. We haven't seen any of those either.
Any other questions? That goes back to the thing. I mean, our theory of gravity and our theory of quantum fields, of the rest, well, the rest of what we know. I mean, we don't know anything about dark energy. But the rest of what we know, and we have candidates for dark matter, but are in conflict. They're not tied yet.
Any question? Bill?
You were showing the values for the decay by Z, et cetera. If those line up, then effectively the Higgs explains all the different masses. Is that what it means?
Well, it means we expect the Higgs to decay. Oh, I'd have to go back quite a ways, maybe? I don't know. But I have this plot showing all the different decay modes. At the beginning here. And you'd expect the Higgs. Well, it's further back than I thought. Must be the next one. Here. We think in this region at 125 that the Higgs, if it's a this is what you'd expect for a standard model, exactly. So you pick a mass. The Higgs should only have one mass, so there should only be one type of Higgs. And it should decay to all of these different things. To BB bar, these are quarks. To photons, to taus, to Ws, CC bar. Photons, by the way, I'm sorry, GG, this is gluons? And then these are the photons. CC bar is down here. So we should see a pattern. We should be able to look for all these things and see a pattern that matches up at one mass, but it's hard for us to do that. Now, the ones we see the best are the photons and the Zs. And we've checked those, and sure enough, they line up. Right at the same mass, we see an excess, but we're seeing more photons than we're expected. And that, like I said, is not significant. If you combine the two experiments, it's 2.2 sigma, something like this. So it's not huge, but if it sustains, if that excess in photons doesn't change by the end of the year, when we have 3 times more data than what I've shown here, that becomes 4 sigma. And then we have something pretty interesting.
I think maybe the question is slightly different, because you're talking about the decay characteristics. And I think maybe his question, if he didn't ask it, I'll ask it, which is you know, the mass of any particle, like the top quark, would depend on the coupling of that particle to the Higgs field. And is there a way of predicting the strength of those couplings?
Is that what you meant? To predict these values, we predict these based on the mass, because the Higgs produces, I mean, the Higgs engenders mass, and so we can predict the coupling based on the mass, but we don't have a fundamental prediction of those couplings, or why those masses are what they are. That's what I said very early on.
So the fundamental reason why the top weighs so much, has so much, is okay, we use those coupled strongly. Okay, like the neutrinos, we don't know why, you know, we can't predict the masses, we can't predict the hierarchy. So as far as I know, the high energy physicists, I'm just the secretary of energy, but the high energy physicists can chime in if I said something wrong.
By the way. There are some interesting theories coming out that say that there is this kind of idea of a 5th dimension, and that there are these brains that, and it was quite interesting is you find that you can predict these couplings based on the overlap of the wave functions in this weird space. We'll have to see.
So far this looks consistent with the standard model, which
Yes.
you express some disappointment about sometimes. In refining this and seeing things like branching ratios and so on, what are the chances are that you will find something inconsistent with the standard model?
You know, we don't know. I was saying that right now things are not very precise. We just reached the point where we know it's there. So that just, you know, at that point, if you just reach 5 sigma, it's very unlikely you have enough data to start studying the properties. On the other hand, we have studied them to the extent we can, and there are some inconsistencies. The Higgs to tau-tau channel we looked at is 0. There's no indication of any signal at all, and we come very close to ruling out the standard model, just in that channel alone. The photons, as I mentioned, were too high. There were too many photons. In fact, we wouldn't have made the discovery as early as we did if the photons were at the standard model level. Remember, we were expecting about 3 sigma, and both experiments got 4 to 4.5. But it's still low statistics, so the uncertainties are fairly high. So as I said, for the photons alone, if you combine the 2 experiments, we're at 2.2 sigma, something like this, just roughly speaking. We haven't done this carefully, so this shouldn't go out into the newspapers and things. It probably will, so I'm going to get in trouble. But it's around 2 sigma. With 3 times the data, you multiply by square root of 3, it's 1.7, and you get to 3.5 to 4 sigma. Then that's pretty significant. So by the end of the year, we're all kind of waiting for the end of the year. It's going to be like opening Christmas presents, What have we got? We really don't know. And we will know a lot more, but those results come out in March. Now we have an intermediate set of results coming out in November for the Kyoto conference with double the data, which will already do something. Then we go to triple. And then we wait, because the machine shuts off for 2 years to repair, so it can go to higher energy. And then we get lots of data. And we think we can measure all of these things to about 10%, maybe even 5%, okay, by 2017. It takes us a long time to do these things, because this is a really rare process. So again, this is 1 in a trillion collisions, and we've had, in 3 years, about 1,000 trillion collisions. So it took us 3 years to produce 1,000 of them. of which we could only detect a couple hundred. So it's slow going. But
All people think, yes?
Just a question about your early work. Do you see any future for magnetic monopoles?
magnetic monopoles, I did this as a graduate student. There was a candidate event that was so spectacular. Everyone believed that it was there. There were like 800 theory papers written. I did an experiment with 200 times the surface area. They killed it completely. And then you become famous for, having looked for this strange particle. Kind of a little wacky thing. We do look for them, actually, at the LHC. And all the accelerator experiments. They take the beam pipes out after they've been used, and they grind them up, and they send them through quantum interference devices, trying to see if there are any trapped monopoles and things like that. But we've had no evidence anywhere, unfortunately. We look for a lot of things that aren't there.
Wait, there's a speaker coming to you. Thank you.
So the two experiments, CMS and ATLAS, are they in any sense complementary as far as the way they do the analysis or the technique, or is it pretty much the same method that two different groups are using?
We're complementary in many ways. The detectors actually use different technologies, but achieve the same, more or less the same performance using completely different technologies. So you have different systematic uncertainties. Okay, that's one thing. The analysis techniques are a little bit different as well. On the other hand, as we see each other present our results, if somebody on the other side had something interesting they were doing that was very powerful, we'll adapt it, and so we'll adopt it, and vice versa. But they're different people. It's different, completely different data, don't forget. So to some extent, they are complementary. But we really need the two to corroborate any kind of finding this profound, for example. But they're probably, I think that's all I can tell you about it, basically. Somewhat, yeah.
Okay, first, just kind of a comment. Fabulous talk, fabulous work. I think the idea of something this complex, it's huge, complex, there are things that they did not go into that really pushed the frontiers in materials and engineering and electronics and everything. It was done, and it worked. And it's an amazing thing when you have these really literally 10,000 plus on both, and then you add to the accelerators, something that complex can actually work. And the more you get into the deals, the more awesome it looks at how can something so huge, so complex, so complicated actually work. Is an amazing thing. Let me just end on this note on Christmas presents and Swiss chocolate. They got a big Christmas present a little bit before Christmas. They got what they wanted. But the best Christmas presents are surprises in the boxes that, in a certain sense, we want a surprise. We desperately want to see supersymmetry or something else. Because if we don't have that, as clearly explained, we got other questions, other problems that we don't know anything about. And even if we do get supersymmetry, that's good, because then it'll give us another set of problems that we know nothing about. And so on Swiss chocolate, so you now know that Swiss chocolate has more energy, kilogram for kilogram, pound for pound, than TNT. But now you will have to ponder this. What's the powerful force field that a few moments on your lips become forever on your hips? And what are the forces that ended up depositing that energy there? All right. Anyway, thank you very much.
Thank you.